Okay, so welcome to my course on fundamentals of electrical engineering. In the fourth module, we were discussing the fundamentals of signals and systems. We had been through the classification of systems in general using a pair of signals, wherein signals again are of several classes. Mostly we discussed continuous time systems, continuous time signals, and based on the continuous time signals, we identified what are the linear systems, the linear time invariant systems, as also causal and stable systems. And the linear time invariant systems were useful for us in the sense that analysis is better, and mostly all the Laplace transform benefits can be made use of, just as Fourier as also Z transform in a different context altogether. But of course, for both for continuous time signals as also for discrete time signals and systems, because with signals you describe systems, so they come together. Okay, so they come as a package deal. We also looked at a very versatile tool, which was the convolution. And now we are, of course, convolution is again applicable to Laplace transform, Fourier transform, Z transform, and whatsoever. Okay, so in that sense, the benefits are universal. Most of the analysis tools, the benefits that come with them happen to be universal, and they are parallel in nature. Okay, so now we will go a little more into Laplace transforms, because Laplace transforms happen to be more or less the fundamental tool that can be utilized. And it's very interesting to see that you can take the Laplace transform based on a very interesting understanding, just like the convolution, wherein a signal can be trapped inside e raised to minus st, where s is both the attenuation component as sigma, and then the oscillatory component with omega entered within. And then we also have the window going from minus infinity to plus infinity if it is two-sided. Otherwise it's zero minus to zero to infinity, such that it becomes then it becomes one-sided. And so we have unilateral Laplace transform emerging out of it. But these classes are not for discussing the theoretical components. They come automatically along with the questions that we discuss that have come in the gate context, because those questions happen to reveal the fundamentals in a better manner. So let's look at some of the questions. In this case, we have to find the Laplace transform of ft to the square root of t by pi, which is given as equal to s raised to minus 3 by 2. And based on this this knowledge that is given, we are supposed to find out the Laplace transform of gt, which is equal to square root of 1 by pi t. Okay, so the just a comparison is enough to tell us that here we are having here we are seeing that the differential of ft. Okay, first and foremost, we take out the square root of pi, so it becomes 2 by square root of pi. And then what do we have? We have square root of t, and what is the differential of square root of t? It's the same as equal to 1 by 2 root t. Okay, so 1 by 2 root t, so that 2 gets cancelled, the pi is retained, 2 comes on the denominator. That's exactly what has happened when you compare ft to gt. That just taking the differential is enough. So, and the the Laplace transform of 2 square root of t by pi is given as equal to s raised to minus 3 by 2. In that case, what do? You just need to take the differential of s raised to minus 3 by 2 to obtain the Laplace transform of the differential of ft. So it's the same as equal to s raised to minus 1 by 2, as simple as. Or when you take the differential, what do you mean? You multiply it by s. Okay, so that's how you take the differential of Laplace transform. So multiplied by s, so we have s raised to minus half emerging in a very simple manner, just through the understanding or the goodness of your eye, where you compare ft and gt. Okay. Similarly, the unilateral Laplace transform, where we take the integral from 0 to 0 minus to infinity. Why 0 minus? Such that we can pick out the initial condition happening between 0 minus to 0 plus. Okay, so that's how it can be explained. So unilateral Laplace transform of ft is 1 by s square plus s plus 1, the unilateral Laplace transform of tft. So just as we did in the question that we right now investigated, we see that when you multiply by t, what happens is that you can take the differential of of the Laplace transform of ft or fs. Okay, but of course you have to multiply it because it's the first differential, so minus 1 raised to 1. So if it's the kth differential, minus 1 raised to minus 1 raised to k, and of course the differential, the number of times that you take the differential also increases. Okay, so here you are having, of course, there's a minus, and then what do you do? So when you take the differential of fs with respect to s, you take the differential of ft with respect to t, you take the differential of fs with respect to s, so it's going to be minus 1. So there are two minuses, so they can cancel. So 1 divided by s square plus s plus 1 whole square multiplied by 2s. So now the differential of the whatever is in the denominator, so we have 2s plus 1. Okay, so the answer D, it seems to be the answer D is the correct option that we pick as the correct answer in any examination context. Okay, so that's just an added knowledge with respect to what we discussed earlier. That is, when you're given ft, you're given the Fourier the Laplace transform of ft as fs, and if you want to find out the Laplace transform of t ft, you take the differential of fs with respect to s and multiply it by minus 1 raised to 1. Okay, and so you reach the answer very quickly. Okay, so now moving on to question number 3. Let ys be the Laplace transform of the function yt, then the final value of the function is. Okay, so there are two theorems. One is the final value theorem and the initial value theorem. They are very much related. If you have fs multiplied by s, that's the first step. Okay, and if you allow, and then when you take the limit as s goes to infinity, you get the initial value. On the other hand, if you take the limit as s goes to 0, you get the steady state or the value at infinity. Okay, so you call it as the steady state value or f infinity. Okay, so in this case, ys is the Laplace transform, and you are supposed to find out the final value. Okay, so you multiply ys by s, so s by s, and then allow the value of s to go to 0. Okay, so option C explains the final value theorem. Okay, moving on to the fourth problem. The Laplace transform of ft is fs, given that fs is equal to omega divided by s square plus omega square, the final value. Okay, so we were talking about final value again. So multiplied by, so fs can be multiplied by s, and then you can take s is equal to, and then you can take the limit as s goes towards infinity. Okay, so s goes towards 0. So there's a problem here because fs is omega divided by s square plus omega square, wherein we realize that ft is going to be sine omega t. Okay, so if sine omega t does not have any value at infinity, it just continues. Okay, so we see that it's neither infinity nor is it 0 nor is it 1. It's none of these. Okay, so that's why we say that if you are having something like this, we say that it is marginally stable because the value at infinity is not available. Okay, so let's go to the next problem. Okay, so almost all important things that we need to remember and know and also apply in the GATE examination context are covered in the GATE exam, in most of the questions that have occurred over the years. Okay, just as in the fifth question, let the Laplace transform of a function ft which exists for t greater than 0 be f1s. Okay, so we are given the Laplace transform of ft as f1s, and the Laplace transform of its delayed version. So we are delaying it by, so if ft is giving us f1s, then f t minus tau. Okay, so or we are delaying it by tau. Okay, that's what is given, be f2s. So what do we do? So we realize that f1s and f2s are connected by e raised to minus tau s. Okay, so let f1s be the complex conjugate of f1s. Okay, so if f1s is given by s plus some, okay, as a function of s, if you replace s by sigma a plus jb or something like that, so in total you will get something like a plus jb. Okay, capital A plus jb. Okay, so if or a minus jb. Okay, so let f1s be the complex conjugate. In that case, f1 star s is the same as equal to, which is the complex conjugate, will be a minus jb. Okay, f1s with the Laplace variable example, set as S is equal to, so S is set as equal to sigma plus j omega. Okay, if GS is equal to F2S, okay, what is F2S? F1 is delayed. Okay, that is the Laplace transform of Ft after delaying it by tau. Okay, so F2S, F1 star S, and what is F1 star S? It's the complex conjugate of F1S, okay, divided by F1S, the magnitude multiply squared. Okay, then the inverse Laplace transform of GS is what? Okay, so first we remember F2S as equal to e raised to minus tau is F1S. Okay, and then you multiply F1S, that is F2S by F1S complex conjugate. So what happens now? We see that e raised to minus tau is there. F1S, let's say, is a plus j omega. In that case, F1 star S is a minus j omega. So when you multiply them together, okay, of course, everything put together, so you are having a square plus b square. Okay, in the denominator too, we have the magnitude. What is the denominator of a plus j omega? It's of F1 s or a plus j omega. It is square root of a square plus b square. Okay, and then what do you have? You take the square root. Okay, and then on the denominator you see square. Okay, so both the a square plus b square on the numerator and denominator cancel. Very simple. And so we are left with only e raised to minus tau s. So what is the Laplace inverse of e raised to minus tau s? It is 1 multiplied by e raised to minus tau s, which is being inverted, okay, into time domain. So what do we have here? We have the Laplace transform of delta is going to be 1. Okay, or the Laplace transform of step input or unit step input is 1 by s. Okay, only of Laplace or only of the impulse, the Laplace transform is going to be 1. So 1 multiplied by e raised to minus tau s tell us that the Laplace inverse of 1, what is that? Delta t, that has to be delayed by tau. Okay, so delta t minus tau is the most correct answer. Okay, once more, if you see as we go along, we see that if F1s happens to be the Laplace transform of Ft, then Ft minus tau will have a Laplace transform as given by e raised to minus tau is F1s, and F1 star s is if it is the complex conjugate of F1s. In that case, if F1s can be imagined as a plus j omega or a plus jb, okay, let's call it as a plus jb, then F1 star s will be a minus jb. Okay, so if you multiply them together, you get what is called as a square plus b square. Okay, and you also, so since if so on the numerator of GS, we have not just a square plus b square, we also have e raised to minus tau s, because it is F2s multiplied by F1 star s, where F2s is equal to e raised to minus tau s F1s. Okay, on the denominator we have the magnitude of F1s, which is the same as equal to the magnitude square. So the magnitude is given by square root of a square plus b square. When you square it, the numerator and the denominator both have a square plus b square. You cancel them, so you are left with e raised to minus tau s, or 1 into e raised to minus tau s. Okay, so you take the Laplace inverse of 1, which is equal to delta t, then apply the delay as delta t minus tau. Okay, as simple as that. Okay, so based on this, let's go to the sixth problem, where we are seeing that a function yt satisfies the following differential equation: dyt by dt is equal to yt is equal to delta t. Okay, so once you see this, immediately what we should do in the gate context is to take the Laplace transform both sides. So what do we have on the left hand side? We have s plus 1 ys, and on the right hand side you have the Laplace transform of delta t is equal to 1. So that's the reason why Laplace transform is packaged and given to each of these students, each of you students, such that you can always use it wherever applicable. Okay, so now a function yt satisfies the following differential equation. So we know that we have ys as equal to 1 by s plus 1. Okay, because delta t has a Laplace transform is equal to 1. Okay, where delta t is the delta function, assuming 0 initial conditions and denoting the unit step function by ut, yt can be of the form. Okay, so yeah, so we have so you have to take the Laplace inverse of of 1 by s plus 1, which is the same as equal to e raised to minus t. Of course, it starts off only at t equal to 0. Why? Because e raised to minus t happens to be for decaying nature only on the right hand side, only when the right hand window is opened using ut. Okay, because the left hand side, it grows, it continues to grow. Okay, so that's it. So let's move to the next question, where in the seventh one, for the equation x double dot t plus, so double dot, as was mentioned earlier, is always telling us the differential with respect to time, okay, which is applicable to signals and systems. It is applicable to control systems, okay, because now we are talking about a dynamic system, dynamic with respect to time, okay. So x double dot t plus 3x dot t plus 2xt equal to 5. So what do? You take the Laplace transform in your mind and you immediately store xs as equal to 5 by s, okay. Remember, 5 is 5 times the unit step input, so 5 by s, okay, multiplied by 1 by s square plus 3s plus 2, okay. The solution xt approaches which of the following values as t tends to infinity. So we have xt as equal to a Laplace inverse of, as I said earlier, 5 by s square plus 3s plus 1. So 3s plus 2. So what we need? We need the value of t as xt as t tends to infinity. So what do? Multiply by s. Okay. Final value theorem, multiply by s. So cut off those s and then substitute for s as equal to 0. Okay. So we have 5 by 2. And so the answer is, so we have on the numerator only 5, on the denominator all the s's vanish, we are left with 2 only, so 5 by 2. Okay. So moving to the last problem, in this last slide, the Laplace transform of a function ft is fs is equal to 5s squared plus 23s plus 6 divided by s into s square plus 2s plus 2. As t tends to infinity, what is the value that ft approaches? Okay. Of course, multiply by s, cancel out those s, then substitute for s is equal to 0. Okay. So what do we have? We have on the numerator only 6, on the denominator we have only 2. 6 by 2 is equal to 3, as simple as that. So we looked into final value theorem. Mostly, we also looked into the complex conjugates and how it can be utilized. We also observed the difference between the Laplace transform of an impulse and a delayed impulse, as also a unit step function, as also a delayed step function. Okay? And we also saw that at infinity, we do not have any values or we do not have a steady state value for sinusoid function. So both omega divided by s square plus omega square as fs or another gs given by s divided by s square plus omega square will give us in its Laplace inverse version a sinusoid, okay, of the sine function or a cosine function nature, and they don't have any values at infinity. You can't say anything, okay. And then we saw that anytime we have a multiplication by t to a function ft or signal ft, then you take the Laplace transform. Then you take the differential of fs with respect to s and then multiplied by -1. Okay, so as simple as that. Most of the details that are covered are known to you, but it's today's session may have been a little bit of a revision for you, and I hope that the succeeding sessions in Laplace transform will also be very much useful for you. Okay, thank you.